Hello. So, this lecture is a continuation of the last lecture on time integration scheme. So, as we have discussed in the last lecture that a time integration scheme can be of two forms. So, one is called the direct time integration scheme and the other is called the indirect time integration scheme. So, the direct time integration scheme, in direct time integration scheme what we do is that we solve this ODE, okay, or we solve this equation of motion directly. So, we will solve this in terms of u. So, the solution is going to directly give us u. So, any finite difference scheme is a direct time integration scheme. There are other direct time integration scheme like Newmark's time integration, Wilson theta method, which we will talk about in detail later. So, the other scheme that is available is called the indirect time integration scheme. So, in this scheme we do not solve u directly, instead we solve this in terms of a different set of variables, and once we solve for a different set of variable, we then from that set of variable we find out the actual needed set of variables, that is u. So, modal analysis or modal superposition theorem is one of the classic example of indirect method. So, in modal analysis we have seen that we write u as modal matrix phi into eta, okay, and this we plug into the equation of motion and we get the solution in terms of eta. So, once we get the solution in terms of eta, we can get back u by using the inverse transform of phi or using the inverse of phi or other techniques to find out E. This we have discussed in detail earlier. So, modal analysis is a classical example of indirect time integration scheme. Other indirect time integration scheme are solution using Fourier transform, Laplace transform, and nowadays wavelet transform. Okay. So, in this kind of techniques we solve the equation, we do a Fourier transform to the degrees of freedom u, and we solve the system of equation or the equation of motion in terms of the transformed coefficient or in terms of the Fourier coefficient. Once we solve the system in terms of Fourier coefficient, we get back the real degrees of freedom by using an inverse transform. Okay. We will not talk about Fourier transform and this indirect time integration scheme here. We will mostly talk about direct time integration scheme because these are more popular than this. Though I should mention here that indirect time integration schemes are also used very often by several researchers for solving certain special class of dynamics problem or special class of vibration problem. So, let me move into the details about direct time integration scheme. So, direct time integration scheme can be of two forms. One is the explicit time integration scheme, one is the implicit time integration scheme. In explicit schemes, the solution at a time instance is obtained using the differential equation or the equation of motion in this case at a preceding time instant. So, suppose I want to know u I plus 1 or u p at time instant I plus 1. Okay. So, to obtain the response at t I plus 1, I am going to solve the equation of motion at time instant I. And this will become more clear as we go into the details of the problem. So, central difference scheme is a classical example of explicit time integration scheme. There are implicit time integration schemes which on contrast to the explicit time integration scheme, they in order to solve for one time instant t I plus 1, they use the equation of motion, they solve the equation of motion also at t I plus 1. So, let me just clarify this a bit later. So, apart from the previous classification, there are two more classes in which this time integration schemes can be differentiated. One is called the conditionally stable schemes and other is called the unconditionally stable schemes. So, in conditionally stable scheme, the time integration schemes, sorry, this is del t. Okay. The time interval that we adopt, del t, should be smaller than a critical value. It should be smaller than a critical value in order to get a stable solution. If del t or the time interval is more than a critical value, then the solution is going to get unstable or it is going to get diverge or spurious. Suppose this should be the ideal solution. Okay. Instead of that, if I have an unstable system, if my del t is greater than del t critical, if I am using an unconditionally stable system, it will instead diverge or it will become it will kind of grow as time gets more, okay, or there would be spurious solution of the system. On the other hand, unconditionally stable system does not has this requirement that del t has to be lower than certain del t critical. So, finite difference scheme is one example of conditionally stable system and certain Newmark time integration scheme is an example of unconditionally stable system. So, now let me quickly talk about central difference scheme, which is an explicit time integration scheme and conditionally stable time integration scheme. So, what happens is that what we do here is that we write u double dot I, the acceleration at the ith time instant. So, this is acceleration at t I or the ith time instant in terms of the displacement at I plus 1, displacement at I and displacement at I plus 1. Similarly, I can write the velocity u dot I also in this form. This is nothing but a Taylor series expansion and the error that we get is del t square because of this approximation. Now, what we are going to do is we are going to substitute this into the equation of motion containing into the equation of motion, which is m u I double dot plus C u dot I plus k u I is equal to f I. So, these are all vectors and these are all matrices. Okay. So, this is at the ith time instant. Or at Ti. Now, what is going to happen is that I am going to plug this 2 into this equation of motion. Okay. I am going to plug this into this equation of motion. If I do so, I am going to get. So, what I have done, I have just substituted this in place of u double dot I, u dot I and ui is of course there into here. If I do this, then I can write ui plus 1 in terms of the preceding value ui and ui minus 1. So, assuming that ui and ui minus 1 are known, I can solve for ui plus 1. So, solution is going to give me ui plus 1. Solution is going to give me ui plus 1. So, what we are doing? We are using the equation of motion at the ith time instant using Taylor series expansion for the displacement and velocity and writing ui plus 1 in terms of the preceding values of displacement ui and ui minus 1, and so this equation is going to give me ui plus 1 provided ui and ui minus 1 are known. So, therefore, this is called an explicit scheme, because in order to solve for the ith time instant, I am using the equation of motion at the preceding time instant, that is at I. Now, I know I should know the initial condition. I should know the value of u at t equals to 0 and the value of u at t equals to 1. Once I know these two values, I can find out the response at u equals to t2. Okay. So, I should know t0, I should know t1. I should know u at t0, I should know u at t1. If these two are known, I can get the value at u t2 and so on. If so on, I will keep knowing the next value and therefore, I will know the entire time response of u. Now, this system is conditionally stable and the delta t that we have considered should be less than delta t critical, which is Tn by 2 pi. What is Tn? Tn is the time period of the highest mode of the system. So, if it is a time period of the highest mode. So, if it is a 5 degree of freedom system, then Tn is equal to the time period of the 5th normal mode or 2 by pi into omega n. So, I have to find out the highest natural frequency, I have to find out the time period because of the highest natural frequency, that by pi is my T critical and my del T should be less than del T critical in order to obtain a stable solution. Otherwise, the solution of this scheme is going to become unstable. The last example that I am going to talk about is the Newmark time integration scheme. So, here again similar to the previous case, I am going to use this approximation for the velocity at I plus 1 and the displacement at I plus 1. This delta and alpha are nothing but constant, and this will be plugged into So, once we substitute this here, after doing some simplification, this equation will help us to solve for u I plus 1. So, I am not writing the intermediate steps which are very complicated, which are very large and cumbersome. You can always look into the references that I have mentioned to get into the detailed calculation. So, we can find for u plus I plus 1, and since we are using the equation of motion at I plus 1th time instant to obtain the solution for u I plus 1, this is called an implicit time integration scheme. So, this scheme is unconditionally stable, that is, we have no criteria on the time interval del t if we choose the parameter delta and alpha as 0.5 and 0.25. For other values of delta and alpha, this system is conditionally stable, or there is a criteria on the time interval del t, so to ensure stability of the solution. So, with this we are going to end today's lecture. So, this is the last lecture on multi-degree of freedom system. From the next lecture onwards, we will move into continuous system. Thank you.